Okay, here we are at day 31. So we're going to get going ahead now. Oh, that's the wrong deck. Okay. Yeah, so I guess we'll just dive on in. We're at the section now where this is the second one. No, that's the second. Okay, we're at the section now where we should be able to make a little bit more, make progress a little bit more quickly. We're getting through the concepts, or getting to the concepts for which I feel like I have understanding present to be able to zip through them. By zip, I mean we know it's going to take longer than anticipated, but it'd be like that sometimes. Okay. So we'll get started here. I think I'm actually take my jacket off. I'm a little hot. Okay. I'm still in econ. I must have added this to the wrong deck. Oh, I was not clicking. Okay, never mind. I was clicking the default deck instead of calculus. So I only have 12 today. It's a dub. Okay. To find inflection points, you first evaluate the first order derivative at points where it's equal to 0, and you plug those into the second order derivative, and the points that result are the inflection points. Or no, I just got to think through it. I think that's incorrect. Okay, so it is the case that finding where our slope is equal to 0 will get us points of transition. And so if we go to the second order, so this is the rate of rate of change of the rate of change. And so if we plug in those initially 0 points, the rate of change of the rate of change Yeah, I think it's actually just the first order, or the first one. Let's see. No. Okay. Yeah. I'm thinking of min or local or yeah. Okay, this makes sense. Because the second order derivative is the rate of change of the rate of change. The issue, and that is the crucial thing, because if we only use the first one, and I think I described this before. If we only use the first one, right here, this is an inflection point, this is an inflection point, this is an inflection point, right? But these, this one would not be registered as an inflection point because we go from we'll say it cuts off here. We go from a small slope to a larger slope. So we don't have a 0 transition point. But if I were to graph this at the second order, so this is the first order derivative here. If I were to graph the second order derivative, it would look like this, where we have, let's see, so it goes up. Yeah, and so I think it would evaluate to something like that. where the slope of the slope increases, and then it hits an inflection point, and we see that inflection point here, and then the slope of the slope increases again, and likewise. So it's sort of enables us to be able to get what we're looking for. If the function is not a exponent of x, a power of x, because we need to include logarithms. A power of x. The power is the general term for exponents, logarithms. Okay, the antiderivative of the cosine of x. I think that's a negative sign. Oh no, it's just sine. Okay, I feel like I'm going to have a difficulty remembering these. Yeah. I could evaluate them. If I do evaluate them, it's likely... Sorry, by evaluate, I mean like derive them. If I do that, it's likely that I will not forget. Yeah. Or I could just come up with rules of thumb. Or not rules of thumb, with mnemonics. I think we'll try that for now. So we'll say like the opposite of cost is sin. In calculus, how do you find slanted asymptotes? This is where the numerator is 1, the leading coefficient in the numerator is 1 power higher than the denominator, and then you do long division, and whatever results is your asymptote. Yep. The quotient rule in calculus. Oh, this is the other one. So this is how you get two functions. Sorry, this is how you get the derivative of two functions that where one function is being divided by another. So we'll say function v and function w. Okay. I can't recall which one is above. Actually, I think it's w is above and v is below. But it doesn't matter for the sake of they're substitutable, right? So if I'm recalling correctly, it's f of, let's see, maybe we'll do, okay, so we'll do v of x and w of x. Okay, so for the given v of x over w of x, we're going to have v of x times w prime of x minus v prime of x times w of x over v squared of x. We'll see if that's correct. Okay, so u prime of x times v of x. Okay, I think I got this right. Wow. Okay, I'm going to adjust it. Oh, wow. Get this little pop-up, eh? Okay, I am going to adjust it just to make it a little bit easier. So I am changing this to be the numerator, n of x, and this to be the denominator, d of x, just so when I interact with something like this here, it's clear. Numerator, denominator. It's clear what the functions will result to be. Or sorry, it's clearer. It would be easier for me to come up with this function because I understand it in terms of numerator function and denominator function. Okay, this is numerator. We got denominator and denominator. Okay, so this should be much easier to recall now. That one was quite labored. I think I'm going to just send it to good, 4 days out. Okay, I think Lagrange notation is the notation we're familiar with, or most familiar with the prime notation. So f prime of x is the derivative of f of x, and f prime prime, or f double prime of x, is the derivative of f prime of x. Whereas Leibniz is, I think, in like it emphasizes the form of the derivative emphasizes rates of change. So it's something like x over y kind of thing. Let's see if that's correct. For Leibniz, yeah, dy over dx shows the derivative as a ratio of changes in y of x. Lagrange notation, f prime of x. Okay, so it's y over x instead of x over y. So I'm going to send that through again. Okay, how can you rigorously find the domain? So you find the domain of a function by determining the areas in which it is defined. So the easiest way to accomplish this is to determine what numbers are not defined for the given function. If they're all defined, then you know that you have like a complete domain. Identify all real numbers where the function is defined. Okay, perfect. How do you find a vertical asymptote for non-rational functions? So you're going to look. You're going to merely look for places where the result, or the result of the function gets arbitrarily close to positive infinity and arbitrarily close to negative infinity at finite values. Particularly look for places where you are undefined. Undefined or discontinuous. Yep. Okay, how's an indifferent integral fx dx expressed in terms of antiderivatives in calculus? Okay, so in an indefinite integral is f of x plus c. Okay. Horizontal asymptotes for non-rational functions. So you're looking for so my current understanding is that when we have powers that are higher in the denominator, like a powers of x that are higher in the denominator, we're always going to have a horizontal asymptote, and it's going to be at 0. However, if they're equal, then you'll still have a horizontal asymptote, but it will be the difference between, or the difference of the leading coefficients. Without like using that approach, because I believe for non-rational, no, I think, yeah, that would be the approach. Let's see if I got that wrong. To find horizontal asymptotes of non-rational functions, compute. Oh, okay. This is the best approach. Yeah, so it's just the generalized case that for the horizontal asymptote, we just compute the limit at infinity. And if we reach a finite value L, we're at a horizontal asymptote. Okay, let's see. Okay, for the mean value theorem, why do we need to be continuous on a closed interval and differentiable on an open interval? Because if it is the case that there exists a point for which, like a tangent line point, a point for which whose tangent line matches the slope of the secant for a given function, the point has to exist, so it needs to be continuous. And because we're differentiating, because the tangent line is a differentiation, we need to be able to be differentiable. Doop, 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 doop. Yep. The chain rule in calculus. This is an approach for evaluating a function. Sorry. This is an approach for getting derivative of composite functions. So for f of g of x, it would be f prime of g of x multiplied by g prime of x. Bum. Okay, a jump discontinuity is when this is one that's not removable, and we move from one value to another. This can occur in piecewise functions, or can occur when something is like undefined. Okay, that was incorrect. Okay, so they exist but are not equal. For the discontinuity, I guess they'd also be not equal. Okay, so I was close, but not as exact as I would have liked to be. So we'll send that one through again. When you're not able to use the power rule, when the function is not a power of x. Lagrange is dx dy over dx, and Leibniz is f prime of x. This is when you have the limits taken from either side do not converge at the same value, and they jump. This most typically happens at for a vertical asymptote. Okay. Perfect. Okay, I think I actually will, let's see. I did not get a lot of sleep last night, so I'm wondering if I should take a nap now so I continue working on stuff, or if I should continue. Okay, yeah, I think I'll stop now. So we've just reviewed those, and then tomorrow we'll just dive in and begin grinding away at these problems. I think this week I would like to do some more streaming than just Monday, Tuesday, Wednesday. We'll see how that goes, though. I'll see you guys.